Right, so I'm here to work out quiz 3, problem 1. So in this problem, you were given some state properties of a saturated liquid. So the first step, where is this? Oh, that's going to be a problem. Hey guys, it's just like class. You must feel right at home. We're going to write out the states. State 1 and state 2. So the problem says that you're starting off with 1 meter cubed of saturated water that's at 200 degrees C. It says it's expanded isothermally in a closed system until the saturated mixture is only 30% liquid. It asks you to determine the work produced by this expansion and state whether this is work in or out and draw a PV diagram. So since this is a closed system, or because it's isothermal, we're going to set T2 equal to T1. The only information we were given about state 2 is that the quality is 0.7, so it's 70% vapor or 30% liquid, as the problem statement said. So that was a common mistake on the quiz, is just mixing those up. And so just remember that the quality is defined as the percent vapor, not the percent gas, not the percent liquid. All right, and then it says determine the total work produced by the expansion in kilojoules. So what we're basically finding is just boundary work. This is the one case where when you start looking at problems like this, you do not need to use the energy equation for boundary work when you're given enough information about the problem. And this is one of those cases. So one of the responses to the most difficult concept or difficult topic of this chapter was determining what assumptions and laws to use. So this is a single case where the only physical law you need is to do boundary work, or is to calculate just the boundary work based off of the boundary work equation. Otherwise, usually you'll need to use the energy equation to do some relationships. In this case, we don't know anything about these two states in order to do anything more, so we're just going to jot down that physical law. As you can see, we need to know the pressure-volume relationship, which wasn't given in the problem statement, so we're going to have to work through and see the relationship as we start looking through the tables. So this is a good review for those of you who are still figuring out how to use the tables. So let's start by determining more information about this this state 1 and state 2 substance. So we know that it is a saturated liquid, which means that it has no gas component. It is quality of 0. So we're going to open up to the tables in the back of the book, and we're going to go to the saturated water tables and go to the temperature entry portion of the tables. And here you can see that for 200 degrees C, the pressure, saturation pressure is 1,553.8, and then you also have all of this information about specific volumes and energies, enthalpy and entropy, if you go to the second page. So we'll come back to this in a second. But what we know right now is that because it's a saturated liquid with a quality of 0, then its pressure is going to be saturation pressure at 200 degrees C. So the table said 1553.8 kilopascals. All right, so that's the pressure. And we know we'll need volume information, so we'll jot down the specific volume as well. So the specific volume is going to be equal to the specific volume of 100% liquid at 200 degrees C. So we're going to go to the tables again and just look up the new F value for 200 degrees C, and we'll get 0.001156. So we'll jot that down in our table. Okay, so right now we have enough state information about the properties of state 1. Now we know that it's at the same temperature in state 2, but that the quality has changed. So this is a good time to think about this using a PV diagram. So we're going to draw the phase boundary curve, and we're going to draw a sample constant temperature line. So this is constant temperature of 200 degrees C, and we just looked up the saturation pressure here, which was 1553.8 kilopascals. So state 1 is right on the liquid boundary, the liquid boundary on the left side of the saturated region. So that's right there. And we know that it stays on the same temperature line and switches to a different quality. So state 2 is going to be somewhere here in the middle, closer to the vapor line. So what's interesting when you draw it out is that you can see that it's still on the constant pressure horizontal line. So you know that P2 will be at the same pressure. So that's going to allow us to move forward a little bit with the problem solution method here. So we know we're looking for boundary work, which is defined by this boundary work equation, but the boundary work pressure relationship is that pressure is constant, so you can pull it out of the integral, and then you know that it's just going to be pressure times the difference in the two volumes. So we were given, we have been looking at specific volumes, so we can either convert these into specific volumes or keep them in the volume form. So let's convert them into specific volumes. So remember, specific volume equals the volume over the mass. So if we want to plug in specific volume for volume, volume equals specific volume times mass. So here, that would result in switching these to specific volumes and pulling a mass out because mass is constant. This is a control mass system. Okay, so we have our equation. We know the pressure is constant, so we know what that is. We're going to need to find mass. We looked up the specific volume 1. We need to find specific volume 2. So we have some more work to do before we can plug in. So let's go ahead and find mass and specific volume 2. Let's start with mass. So mass can be determined from this equation here. So mass is going to equal the volume over the specific volume. We have information about both of those for state 1. So we can plug those in. So we know it's 1 meter cubed over the specific volume we looked up in the tables. And that's going to come out to 865 kilograms. For new 2, we're going to need to use the information here to determine new 2. So we know the quality. So remember the equation when you have a saturated mixture is you're going to take X and multiply it by new Fg and add new F. So those are all table lookup values. So X is 0.7, and then again we're just going to go back to the tables. We already used new F, which you found right here, and then new Fg is also in the tables. It's 0.12620. So we'll just plug those in. And when you do that calculation, you'll get new 2 equal to 0.089496 meters cubed per kilogram. So now we have everything we need to find boundary work. So we're just going to plug in all of those things we either calculated or looked up in tables and find our boundary work. So we have 865.052 kilograms. Our pressure is our saturation pressure, constant because it is right on this constant saturation line under the curve. And then plug in our 2 specific volumes. You're going to need to do some unit conversions to get to kilojoules. So we know that a kilojoule is equal to kilonewton times a meter. And then kilonewton over a meter squared is equal to a kilopascal. Once you add that unit conversion, you can cancel out all of your units and you should be left with just kilojoules. And your final answer will come out to actually megajoules. So I could do another conversion to get to megajoules, but I'll keep it off because I'm running out of room. So the answer comes out to 118 megajoules. So that's the boundary work. It's positive, so remember work out is positive. So the answer to the question is work out. It's not so easy to conceptually think about this particular example because there was very little information about what kind of system it is. It just says a closed system, but you do know that it's expanding, so work out does make sense in that scenario. So this is an overview of the first question on the quiz. Hope that helped. Thanks.